those of you who made it back from the coffee break. And I imagine that some more people will keep coming in. This is a session on Cryptanalysis II, which is the best of crypto and of analysis. So I hope you'll enjoy this session with me. There will be 4 talks today, and the first one is on isogeny-based cryptography, which is, contrary to some people's belief, not totally broken. There are still things that are believed to be secure. And the title is Accelerating the Delf Skelbroth Algorithm with Fast Subfield Root Detection, written by Maria Santos, Craig Costello, Josh, and Maria will give the talk. Please.
Thank you. Can everyone hear me? Okay, cool. Thanks for the introduction. So I'm Maria, and I'll be talking about how we accelerated the Delf Skelbroth algorithm with fast subfield root detection. So first, some motivation as to why we study this problem. So the supersingular isogeny problem is the foundational problem in isogeny-based cryptography, and it's conjectured to be post-quantum secure. So primitives like ski sign, which is an isogeny-based signature scheme, and B-side, which is a key exchange, relies on the difficulty of this problem, though slight caveat that B-side might also be affected by the new attacks. And the best known classical attack against this isogeny problem is the Delf Skelbroth algorithm. So our contributions in this paper was to implement and optimize the Delf Skelbroth algorithm to determine its concrete efficiency. And then we developed an efficient method to detect whether a polynomial with coefficients in some extension field of FP has a root in the base field. And then using this, we improved the Delf Skelbroth algorithm by lowering its concrete complexity. Okay, so first some background information. So in isogeny-based cryptography, we study elliptic curves. And an elliptic curve is a smooth curve given by this equation, where you have y squared equals some cubic, and A and B lie in FP squared. And because we normally use cryptographic size primes, we can assume that P is not 2 or 3, so there are no issues with that. And then we have this condition where 4a cubed plus 27b squared is not equal to 0. But all that means is that our curve is not singular and behaves nicely, and you have a nice group law on your elliptic curve. And for efficiency reasons, we study supersingular elliptic curves. And a key point that we'll be using throughout the talk is that we can label our elliptic curves using what's called a J invariant. And this J invariant is given by this equation here, which is also why we need this to not be 0. And your J invariant lies in FP squared. So given an elliptic curve, you can compute its J invariant and use it to label your elliptic curve up to isomorphism. Okay, so an isogeny is then, if you have 2 elliptic curves and you consider a map between them, an isogeny is this map which should be non-constant and should send the identity point on E to the identity point on your image curve. And these properties ensure that our isogeny is a group homomorphism, which just means that it interacts nicely with the group structure on your elliptic curve. So given 2 points on your elliptic curve E, if you add them together and apply the map, it's the same as applying the map on each point and adding them on the image. For all the isogenies that we care about in isogeny-based cryptography, we define the degree of our map to just be the size of its kernel. And then we'll say that an isogeny of degree L is just an L isogeny. Okay, so now I'm ready to define the supersingular isogeny problem. In its most general form, it asks us to find an isogeny between two supersingular elliptic curves defined over fp squared. Note that we're not assuming torsion point information. We're not assuming that we know the degree of the isogeny, or that the starting curve is of any special form with known endomorphism ring, etc. So in particular, it's still conjectured to be post-quantum secure, and it's not affected by any of the attacks, because they really rely on these two points here. Okay. So a nice way to view this isogeny problem is by viewing it in terms of finding paths in a graph. So if you let P be a large prime, such that it doesn't divide the degree of your isogeny, you can define the supersingular isogeny graph, where here your nodes are elliptic curves, supersingular elliptic curves, and you can label each node by the J invariant. And then the edges in your L isogeny graph are just L isogenies. So two nodes in your graph will be connected by an edge if the elliptic curves are connected by an L isogeny. So the properties of this graph that will be interesting to us are that a random walk of short length, so of log p steps, is almost as good as uniformly sampling a vertex. And this is called the expander property. And it intuitively means that there's very good mixing in the graph, which means that finding a path between two nodes is generally quite difficult. And in fact, path finding in this graph is conjectured to be hard for both classical and quantum computers. And as I said before, finding a path between two nodes in your graph is the same as finding an isogeny between the elliptic curves represented by the J invariants. And just sort of a point of clarification, we normally just consider the set of vertices, and we kind of move in between the different L isogeny graphs. So sometimes we'll take steps in the two isogeny graph where we walk along the edges represented by two isogenies, and then we'll switch between graphs with different L's. But our node set will always stay the same. Okay, so sort of a very special property of this graph is that there's a subgraph given by J invariants that are defined over FP. So you have your supersingular elliptic graph, supersingular isogeny graph, and most of these are have J invariants, which are defined over FP squared, and these are the ones that are in white. But there are a subset of these have J invariant defined over FP, and this sort of defines an FP subgraph. And the paths in this FP subgraph are a lot easier to find, or comparatively easy to find. Whereas finding paths between nodes defined over FP squared to the nodes defined over FP is kind of the bottleneck. Like this is takes a longer time. So Delf and Galbraith used this to develop their algorithm, where they have a start and end node, and these are the elliptic curves you want to find an isogeny between. And the first step is to find a path from your start node to a node defined over FP. And then you do the same for your end node. And because of the proportion of nodes defined over FP squared and the proportion of nodes defined over FP, you can expect to do this in sort of order of the square root of P bit operations. And then once you have these two nodes defined over FP, you can find a path between them. And this will take around order of the fourth root of P bit operations. And this is what I mean by it's easy. It's still not easy, but it's like comparatively, this first step is the bottleneck. And then you can just concatenate the paths and find your path from your start node to your end node. And because the first step is the bottleneck, this is the step that we focus on. And from now on, I'll just be talking about how you can go from a node in FP squared to a node in FP efficiently. Okay, so now how do we take a step in this graph? To take a step in the graph, we use modular polynomials. And these are just bivariate polynomials with integer coefficients. And they're symmetric in x and y. And they're of degree NL. Though the details don't really matter. All that matters is NL grows as L grows. And in particular, equals L plus 1 when L is a prime. And the key point of these modular polynomials is that if you evaluate them at 2J invariants, it will evaluate to 0 if and only if the elliptic curves represented by these J invariants are L isogynous. So they're connected by some L isogeny. And so if we evaluate our modular polynomial at J, then we can compute the roots of this polynomial, and these will be the neighbors of that J invariant in the L isogeny graph. And just a really technical point is that we can reduce the coefficients of our modular polynomial mod P, and this ensures that we have no storage issues. Okay, so maybe a bit more clearly, what you do is you store your current J invariant and your previous J invariant. You find the roots of your modular polynomial evaluated at your current J invariant, and then you divide by x minus your previous J invariant. And this ensures that you don't go back to where you came from, so you don't want to sort of backtrack in your graph. And then you choose one of these NL minus 1 roots, sort of at random, and you step onto it and you continue the process. Okay. So our optimized implementation of the Delf-Skelbroth algorithm was used to determine the concrete complexity of the first bottleneck step. So finding from an FP squared J invariant, finding an FP subfield node. And we found that experimentally, this was the concrete complexity of the algorithm. And just on a high level, some of the optimizations we did was choosing L to be 2. And this ensured that this polynomial here was quadratic, so it's sort of the easiest case, and you can easily take square roots. We also optimize the square root, the procedure to take square roots, and things like that. But you can find more details of that in our paper. And yeah, so we found that the concrete complexity was C times square root P times the log P factor, where C is between 0.75 and 1.05. Okay, so now to go on to the new attack, we changed the first step, the subfield search. And the key observation that we made was that at each step in the 2 isogeny graph, you're not interested in the precise values of the neighbors in the L isogeny graph. You're only really interested in whether or not it lies in FP. And so then once you've found a node that lies in FP, you can sort of take the Lth root and actually find its value. But when you're taking steps in the graph, all you are interested in is whether it lies in FP or not. And because this is less information, you could hope to do it more efficiently than computing roots of your modular polynomial. So as an overview, at each step of the random walk, Supersolver will inspect the L isogeny graph using this fast subfield root detection, and it will do this for L in some carefully chosen set. The animation isn't working, but yeah, you can do this for L in a carefully chosen set to efficiently detect whether the current J invariant has an L isogynous neighbor in FP. And so what you want to do is sort of scan a larger proportion of the graph. So if you were just looking at L equals 2 and taking steps in the 2 isogeny graph, then this you would only sort of reveal 2 of the neighbors. But if you could scan a larger proportion of the graph for more L in an efficient way, then maybe you could cover a larger proportion of the graph at each step and find your FP node faster. Okay. So yeah, our fast subfield root detection gives a fast way of detecting whether you have a root in FP without actually computing the roots. So this is sort of the key lemma. If you take the p power Frobenius map, and all this does is it acts on a polynomial f by raising the coefficients to a power of p. Then if you take the GCD of f and this map applied to f, it will have degree 1 if f has a root in FP, and it will have degree 0 if f does not have a root in FP. And you might be wondering, what if the degree is bigger than 1? And in our application of this, that only happens sort of negligibly often, and so we can sort of discard this case and not worry about it. In fact, we discuss in the paper that if that is the case, it's actually sort of a win for the cryptanalyst. And so, yeah, but we discard the case when the degree is bigger than 1 because it happens negligibly often. In the paper, we also show how to transform f and pi of f, which in general have coefficients lying in FP squared, to give 2 polynomials with coefficients lying in FP that have the same GCD. And so you can still compute the GCD here, but instead you have J1 and J2. And this means that you can avoid all multiplications in FP squared. And so it makes our detection even more efficient. So now to discuss how we choose the list of optimal Ls. So though inspecting the L isogeny graph using the subfield root detection does increase the number of multiplications that you do at each step, you are checking a larger proportion of the graph. I don't think the animation will work, but if you want to see it, you can go on the crypto website. But you can compute a list of optimal Ls, which minimizes the ratio of FP multiplications per node revealed. Yeah. So the key point of this computation is that it only depends on the prime. And so finding your list of optimal Ls can be done in pre-computation. And then you can reuse that for every instance that you have. Okay. So finally, our results. We ran a few experiments to compare how SuperSolver performs compared to Solver. And we ran some experiments on small primes and many J invariants. So SuperSolver finds a subfield node with, on average, half of the FP multiplications, and it visits a lot less nodes. So taking example, if we have a 24-bit prime, we averaged over 5,000 instances, and we found that Solver needs around 113,000 FP multiplications, whereas SuperSolver only needs around 54,000, and it walks on a lot less nodes. And this is because at each step, you're covering a larger proportion of the graph, and so you don't need to step as much to cover more nodes. And then we ran some experiments on cryptographic size primes. We ran SuperSolver and Solver until the number of FP multiplications used exceeded 10 to the 8, because you can't actually solve these instances, otherwise it wouldn't be secure. But we ran it until the multiplications got to 10 to the 8 and just recorded how many nodes in the graph are covered. So this is both the nodes that you step on and the nodes that you scan using fast subfield root detection. And we found that for a 50-bit prime, SuperSolver covers around 3 to 4 times the number of nodes that Solver does. And this advantage grows as your prime grows. So for 800 bits, SuperSolver covers around 20 times the number of nodes. And this is kind of an interesting trend that as the prime grows, the advantage of supersolver also grows. And this is because taking a step in the graph, so computing a square root of your modular polynomial depends on your prime p, but our fast subfield root detection only depends on L. So as p grows, you add more L into this optimal set of L's. So you can imagine as p goes to infinity, what you would do is just stay on the node that you're on and scan the graph for all L. So yeah, so finally some conclusions. What does this mean for isogeny-based crypto? We only improve on the concrete complexity, and so the asymptotic complexity of the problem is unchanged. But it does affect concrete parameters that will be used for B-side and ski sign, because these have Delf Skelbroth as the best attack. Again, caveat on B-side, but ski sign, this is definitely the best attack, and so it will affect the concrete parameters that are chosen for ski sign. And for more details, please see our full paper on ePrint 1488. Thank you.
For this very nice talk. Also, thanks for staying within the allotted time. So we're not delaying any further. Are there any questions in the audience? I see one question on Zoom by Jonathan Levin. He's asking, could you elaborate more on the distribution of curves in the L isogeny graph with J invariance defined over Fp versus Fp squared?
So let me just go back to the, sorry. Yeah, so I think this is the photo. So there are around order of p nodes in the supersingular isogeny graph. And so there are around order of p that have J invariant in Fp squared, and only around order of the square root of p nodes that have J invariant in Fp. And there's actually sort of like a clustering effect, I think, where the Fp nodes cluster together in the graph. But yeah, this is sort of the proportion of the nodes in the graph, and this is how you can come up with these sort of running times of the first step and the second step. I don't know if that answers the question, but hopefully it does.
It sounds like it might. He says thanks.
Oh.
I also have one small question. So your implementation was done in Sage, which at your level of analysis doesn't matter because you count multiplications. But are there any plans to make like a serious implementation of this in C or some low-level language?
Yeah, I think, so our motivation towards the Sage was, again, because we only count multiplications, and so you can sort of convert this into any metric you want. But I think maybe further down the line, there are plans to sort of make this sort of software that you can use to determine the security of schemes which have this as their best attack. In particular, I think there are still some optimizations that can be done, but yeah, maybe in the future, but for now, it's just on Sage.
Okay. Thanks again to the speakers.
Thank you.
So I guess while they set up the technology, I can start introducing the next talk. This is kind of a change in topic because it's suddenly about symmetric cryptography and about side channel resistance. But I guess it's still going to be very interesting. The title of the next talk is Secret Can Be Public, Low Memory Aead Mode for High Order Masking, authored by Yusuke Naito, Yu Sasaki, and Takeshi Sugawara. And you will give the talk as soon as they finish setting up the tech.
So thank you for introduction. So I'm Yu Sasaki from NTT, and I'm going to present our paper. So this slide shows the one-page overview. So first, we present a new three-block cipher-based authenticated encryption with associated data mode, which we call HOMA. And HOMA achieves small memory size for higher order masking side channel countermeasures. And the interesting feature is we protect only S over 2 bits of the state, while we prove its security after S bits. And this is HOMA is a mode. So to use it, we need a three-block cipher. And the requirement of the three-block cipher is shown here, but unfortunately, there is no existing three-block cipher that supports this configuration. So we need to design a new Skinny-based TBC instance. And lastly, we implement a HOMA with Skinny EE in hardware. And the results show that HOMA has slightly bigger memory than the state of the art if side channel countermeasures, maskings, are not implemented. But as long as masking is implemented, then the HOMA is smaller than the state of the art for any protection order D. Okay, so let's start the standard part. So in side channel analysis, besides the standard input-output of the function, the adversary can learn some information from implementation features. And the resistance against side channel analysis is quite important. For example, it is considered in the selection of the future standards by NIST. And there are several previous research directions on Aead with masking-friendly Aead. The first direction is leakage resilient cryptography. Those schemes use leak-free component in the part of computations, and the usual goal is to minimize the use of such leak-free components. So they typically aim at optimizing the speed and not the size. So the goal is different from our research. And another topic is like masking-friendly primitive, which is easier to mask. But this is about primitive and nothing special for the mode. And the mode level optimization is not considered in the primitive proposal. So this direction is also different from ours. And the last one is our approach, which is low memory Aead mode. So in this direction, we apply the masking countermeasures to all computations. And we want to minimize the memory size after the masking. So I'm going to explain the masking. So here, the model, the adversary model in this talk, in this research is a probing model. So the adversary probes a wire to get data. Moreover, we assume that the worst case scenario, the strongest adversary, and the adversary can get the full data on the wire if it is probed. And well, our aim is to develop a construction that is strong even for this strong adversary. So how to prevent this adversary? The popular approach is masking countermeasures. The input data is encoded to multiple shares. So then the scheme like secret sharing will run. So the adversary can't recover the original data even by probing a single state. More powerful adversary may probe D wires in the D is greater than 1. But even such adversaries can be avoided, can be prevented by making more shares. And this is called high order masking. And this is a research motivation. Well, we can apply the high order masking, but then the memory overhead is quite huge because the state is duplicated into multiple shares. And there are masking schemes called D+1 masking. And those encode the state into D+1 shares. So this means that after the masking, the memory size increases D+1 times, which is quite big. And this is the motivation that we need a new design that is optimized for high order masking. And so first, let's discuss the minimum state size. I mean, lower bound of the state size. So let S be the target security. Like S is 128 in a real use case. But so we need at least S bits of the key and S bits of the state. Well, otherwise, the adversary can directly guess the key or state with complexity less than 2 to the S. So S bit security is not achievable. Then we apply the masking on this data flow. So the key is expanded to D+1 shares, and the state is expands to D+1 shares. So there is a folklore on the memory size for masking. The total memory size is at least D+1 2S bits. And this is kind of a barrier. And in this research, we break this barrier. The overall idea is here. Well, we don't do anything on the key. That the state, for the state, we divide the S-bit state into 0.5s of protected state, and the other half for unprotected state. The unprotected state is, well, unprotected, so we don't expand the state size into multiple shares. So by this approach, asymptotically, we achieve D+1 times 1.5s bits memory. But of course, I'm cheating in this figure because for this figure, unprotected state is obviously vulnerable, obviously weak. So to make the S-bit state, we needed to mix the value from the protected state and the values from unprotected state. But then it turned out that this mixture is not like a simple. We have to carefully devise new operations to securely mix protected and unprotected values. Okay, so then I'm going to explain how to construct this data processing part. So I first give you general description of the computation with protected and unprotected states. So now the size of the protected state is 0.5 s bits, and the unprotected state is for 0.5 s bits. And those are processed by some function which we call data processing function. And this function also takes associated data block or message block as input. And first, I'd like to show that with the standard nonce-based AE, the construction is generally broken with 2 to the 0.5 s compressivity. So the idea is playing with decryption local. So this slide shows the decryption local data flow for the decryption local. And for any decryption query, unprotected values are leaked to the side channel adversaries, even with an invariant tag. So usually, if the tag, verification fails, then the scheme doesn't leak any information. But if the state is unprotected, and if you can probe the wire, then the side channel adversary can know the value of the state. So more intuitively, the verify then it should be verify, but verify then decrypt approach can't apply to the side channel adversary with unprotected state. So this is the reason the situation is very different from the standard nonce-based Aead. So actually, we can write down some attack procedure that breaks security notion with the 0.5s bit security. So I don't explain the attack procedure here. But the idea is to generate the state collision by changing associated data. And we keep the message same for all queries. And well, in the standard scenario, I mean, in the standard adversary can't detect occurrence of the collision usually. But for the side channel adversaries, and if some state is unprotected, they can detect the collision of the associated data. And so later they can play with encryption query to generate some invalid some attack data. So this is a generic attack. So as long as unprotected state is used, this attack works. So we need additional features to prevent this attack. So the idea here is to use to randomize IV. We force initial value IV to be randomly determined for each encryption query. Then the adversaries can no longer play with decryption record before IV is determined. So the attack I described in the previous page wouldn't work. So I think this gives you the idea that the situation for unprotected state is quite different from the standard Aead schemes. Then I step into the construction of the data processing part. So the scheme is based on tweakable block cipher, which takes tweak as input and converts plain text to the ciphertext. And this plain text to ciphertext conversion is directly updated by using a key. So we need to protect it. Otherwise, the key is directly leaked. And this is quite like suitable for processing protected state of the HOMA mode, because protected state anyway requires protection. And the tweak of the tweakable cipher is a public value. So we don't need protection because it's public anyway. And the unprotected state of HOMA can be processed by the tweak. And also other public data such as nonce counter and the data input can be processed by the tweak. And HOMA applies the protection only for the plain text to ciphertext conversion of tweakable block cipher with 0.5s bit block. But we want to ensure S-bit security. So that means the construction requires kind of like BB beyond the sparsely bound security, BBB security. And there is one previous work which achieved the similar security level, which is called PFP+. And the idea of a PFP+ may help us to ensure S-bit security by using the small block size TBC. And the diagram of the PFP+ is here. Yep. So we have upper 0.5 S-bit state and the bottom 0.5 S-bit state. The upper state is XORed with data input and processed by the TBC. The bottom half is never processed by updated by TBC, but this will impact to the tweakable block cipher computation via the tweak. So this is quite simple. But then one may think about like leaving this part unprotected. I mean, leaving the bottom half of the PFP+ unprotected. But unfortunately, PFP+ is broken if the lower half is unprotected. So suppose that the lower half is unprotected, that means like a side channel adversaries can know the value of this part. So then the adversary can learn the value of V1 and V2. And because of this computation, the value of V3 is easily computed. But the value of V3 is supposed to be protected. So the construction already occurs. So we need some new constructions to keep protected value protected. And so this is the overview of our construction. So the major difference is we call TBC twice to process each associated data block. And a single TBC call generates 0.5 S-bit unprotected value, unpredictable value. And to mix the whole S-bit state, we need 2 TBC calls. And in this construction, we input data input via the tweak. So compared to PAP plus, the tweak size is bigger. That means without any countermeasures, HOMA is bigger than the state of the art, I mean PAP plus. But the size of the protected state is only here, so which is smaller than the PAP plus. So if you apply the masking implementations, then memory size becomes smaller. And this is the construction for the encryption part. We need to call a TBC 3 times to process each message block. And the first take-a-purpose cipher generates a key stream, and the other 2 calls mix the state as in the associated data. And the security proof was done by my co-author Yusuke Naito. And this summarizes some intuition of the proof. The assumption is strong tweakable PLP for the underlying take-a-purpose cipher. And the result is S-bit security, S-bit provable security. And here is the intuition of authenticity. So for each DPF, we ensure that S-bit unpredictable value is produced by iterating the TBC calls. And regarding privacy, we ensure independence of each TBC by properly assigning the nonce and the counter. Okay, so that's about the mode, and we need a tweakable block cipher. And to achieve 128-bit security, so HOMA needs a tweakable block cipher with 64-bit block and 128-bit key and 256-9-bit tweak. Block size and the key size would be okay, but the tweak size is a bit too large. And no existing TBC supports those parameters. And moreover, for the mode, I explained that unprotected values and protected values must be mixed, must not be mixed. And this also applies for the inside primitive. And we found that the tweaky framework is quite useful. But the question is, can we just like extend the previous skinny to support more tweak and key? But unfortunately, there is no efficient way to support such big tweaking. So we need to make some change. But the original tweaky framework is aimed to support variable tweak and key sizes. But this is not important for our goal because the key size and tweak size are fixed. So we drop this feature and we treat tweak and key as independent object. And then the security is ensured by MILP, so some automatic tool. And we also have some minor improvement about the elastic tweak to process 3-bit tweak for the domain separation. And so this is like a one-page overview of the run function. Well, I don't explain details here, but I think this slide would be useful if you check the video later on the YouTube. Then finally, we implement our designs. So we evaluate ASIC hardware performance with HPC2 star masking schemes for protection order from 0 to 5. And we compare the results with PFB Plus, which is implemented under the same implementation policy. And the implementation results are here. So the numbers in the red square shows the gate equivalence of HOMA and PFP plus for each protection order. So in summary, HOMA's memory size is bigger than PFP plus for implementations without side channel protection, without masking. But HOMA is advantageous for any protection order D which is bigger than 0. And this also shows one interesting property. So one may think that only with primitive improvement, the memory size can be smaller. I mean, the mode level optimization may not be so useful. But the answer is no. I mean, mode level optimization is quite useful. And because the improved factor, for example, like 6884 versus 6283, is bigger than the S box size, like 501. So that means our results can't be reached by improving S box of the primitive. So the this is a quite good evidence that mode level optimization is useful. Okay, so I'd like to conclude my talk. So we propose a new TBC-based Aead mode, HOMA, which achieves small memory for high order masking. And we implemented HOMA with a new TBC instantiation and showed that the results perform quite well. And well, one possible future work is to design yet another new modes to ensure S-bit security based on TBC with a smaller block size than 0.5 S-bits. But this is not easy because you also need to develop specific TBC. So this is not an easy task, but maybe interesting challenge for the future. Yeah, that's about my talk. Thank you for your attention.
Thank you for this very interesting and clear talk. Are there any questions in the audience? We have 1 minute or something. Oh, yeah, please use the microphone.
Thank you for your presentation. The HOMA achieves the S-bit security by using 2 states. Do you think the security is improved when we use more states?
Sorry, how much is this bit security by, did you say 2 steps?
S-bit security by using 2 states.
Sorry, 2 what?
2 states.
2 steps.
Status. 2 0.5 S-bit.
Oh yeah, yeah.
Right?
2 states, yes.
The security is improved when we use more status.
Do you consider changing the entire state size? I mean,
Like PFB omega.
security is increased. I mean, by splitting this part into like 3 parts or 4 parts that you're asking, right? And well, as long as the entire state size is S-bits, the maximum security you can get is S-bits.
Use like 2 S-bit state size. If we use 2 S-bit wise.
2 S-bit wise. Oh yeah, so then so S is like a parameter, security parameter. So if you substitute 2S into S, then the security simply becomes S-bits, 2 S-bits.
Thank you.
Okay, thank you.
Okay, so we're out of time for this talk, I'm afraid. So let's thank the speaker again, and then we can have next talk. Okay, while they set up, I will introduce the next talk. This is again on the topic of post-quantum primitives. The title is Partial Key Exposure Attacks on Bike, Rainbow, and True, all of which are post-quantum schemes. And the speaker, who's right here on stage, is André Essa. And the paper is co-authored with Alexander May, Javier Verbel, and Wei-Chiang Wen. Whenever you're ready.
Oh, yes, hello, thank you for the introduction. We were investigating partial key exposure attacks on Bike, Rainbow, and Entru, and this is joint work with Alexander May, Javier Webel, and Wei-Chang Wen. So in this work, we were asking the question if post-quantum candidates are leakage resistant. So what does this mean? In an informal sense, if you have an n-bit secret key and L bit of this secret key get leaked, then we say a scheme is leakage resistant if it offers the security of an n minus L bit key, which is somehow the best you might hope for. And we know from classical schemes that, like RSA, that this is not the case. So why are we asking this for post-quantum candidates? Because the best known attacks so far simply enumerated missing bits, and this strongly supports leakage resistance belief. And so these attacks do not exploit any key redundancy, key structure, or relations between the public and the secret key. And in this work, we give new attacks, which actually heavily exploit those things. And yeah, using these new attacks, we derive bounds on the required leakage to recover the full key. So again, let me give a brief overview of our methodology. So first, we model the leakage that we obtain from some arbitrary side channel. So how does this leakage look like? Here we differentiate two models. And then in each model, we ask first the question for asymptotic leakage bounds. So here the question is, how big has the leakage to be able to recover the secret key in polynomial time? And a more practical question where we are interested in recovering the secret key below some time threshold. So let's say to the 60-bit operations. So how big can or has the leakage to be able to achieve this? And this is basically also the structure of the talk. So we will define the model, and then we will answer these two research questions. But before we dive into the models, let's first get some basics on the secret key structures of Rainbow, Bike, and Entru, which are the three schemes we exemplary investigated as a multivariate code-based and a lattice-based scheme. So here we keep it very light. So I try to abstract a lot of things away. But yeah, in the Rainbow case, we have the secret key is formed as two matrices, so two linear transformations over FQ with this structure here. So basically the secret key is this S prime, T1, T2, and T3. And we show that a single row of S prime, as well as a constant number of columns from T1 are actually sufficient to recover the full secret key. So if you take this definition of the secret key, it inherits a quadratic redundancy factor, which is actually exploited by our attacks. And if we go to the bike scheme, the secret key is formed as a length n vector, which is quite sparse. So it has only a few amount of ones. Sorry, here's something wrong. It doesn't matter. So it satisfies some matrix vector product equation. A times S is equal to E. And yeah, obviously S or E suffice here to recover the other part. So we have a linear redundancy factor here. And last but not least, in the Entru case, the secret key might be seen as a ternary vector of length n. It fulfills a similar equation as in the bike case, but note that E is not part of the secret key here. So we have no intrinsic shortcut. But yeah, current implementations usually store some extra information for efficiency reasons. So there is some redundancy, but definitely the least redundancy here in the Entru case. And we will see that this is also reflected by our attacks. Usually they tend to be better the higher the redundancy as a rule of thumb. So our attacks on bike are actually the easiest to understand without a lot of prior knowledge. So I will use them as a kind of running example to give an indication how these attacks might look like. And they use a technique called information set decoding, which yeah, allows also to recover the bike key without any leakage. Of course, the attack has a high complexity, but then we accelerate this technique by using the leakage yeah, obtained by an arbitrary side channel. And interestingly, we use the information set decoding technique not only in the bike case, but also as a key ingredient for all three schemes to obtain our results. So let us briefly have a look how this technique works. So as we said in the bike case, secret key is a length n binary vector which is quite sparse. That it has only a square root of n number of 1 entries in a length n vector. And of course, it fulfills this matrix vector product relation. So we can also like append the identity to the left of A and then like rewrite it like this. And we visualize it for now compact like this. Matrix times vector is equal to 0. And yeah, then we're interested in finding this vector ES here, this orange vector, without any prior knowledge. So assume for the moment that we would know n/2 0 coordinates in this vector. That's, for example, here, but I just put them in the front and in the back for an easier illustration, but they could distribute anywhere over this vector. So if we know such a set of n/2 0 positions, then of course these parts of the matrix do not play any role, can safely discard them. And so then we're left with a square system, which we can simply solve via Gaussian elimination to recover this vector here, like include the zeros again. And as soon as this vector here has weight square root of n, we're done. But of course, this is not necessarily the case because we don't know a priori such a set of n/2 zeros, so we have to guess one. But of course, it's a sparse vector, so the guessing probability is quite good. And then, yeah, if it is not of the desired weight, we guess a different set of zeros, and until this is of weight square root of n, and then we recovered the secret key. Okay, this is the basics. So now let us get into the model definition. So we start with the erasure model, where so in general we model the secret key always as n bits. So it doesn't matter, like even if it's a matrix, we can always write it as a chunk of bits, and we consider it n bits long. And in the erasure model, it says error model, but it's the erasure model. We get knowledge of an erased key, where yeah, some of the bits got erased, indicated by this question mark covered areas here, and they are not known, but the positions are known, and the green parts are known, as well as the positions, and they're guaranteed to be correct. And yeah, zeros and ones get erased with the same probability. Yeah. And now, given such an erased key, the question we answered is first about the asymptotic balance. So here we have the different schemes and different settings. I will explain in a second what this means. And the question is how many erasures, so how many question marks can we tolerate to still recover them in polynomial time. So for example, in the rainbow case, if we consider the first layer, just a second, then I will explain what it is. We can tolerate n minus something sublinear and n a number of erasures to still recover it. So almost everything basically, which is related to this quadratic redundancy factor. And yeah, so but first, if we perform a basic enumeration, then you can only tolerate a log n amount of erasures, because the enumeration comes at a cost of 2 to the number of erasures, which is only polynomial if the amount of erasures is logarithmic. Yeah, so what is this first layer? So the first layer is basically, if we have this definition of the secret key, then it's this S prime, T2, and T3. And if you recall Ward's talk from yesterday, it's basically this outer layer, which is added by Rainbow to the UOV scheme. And the full key recovery then requires to also recover the key of this smaller UOV instance, which is left. And to recover this, we can only tolerate square root of n erasures on T1. And here we already see that UOV is like inherently more secure against our attacks than Rainbow is. Yeah, and yeah, in the byte case, we separate also two different settings. It's the standard and the compact setting. In the standard setting, the secret key is represented as a sequence of n bits. So just as it is defined like a low weight n bit vector. And in the compact setting, we encode the one positions of this vector. So if you count from the right, this is the compact representation of this vector. And due to this compression, we get a slightly lower number of tolerable erasures. And in the entry case, we also differentiate two cases, two settings, but they matter mostly in a practical sense. So here we have an unpacked and a packed representation. So in the unpacked representation, the coordinates of the vector are stored via 2 bits each, which is wasting some of the bits. So there is an encoding which actually packs a certain amount of this into a more dense representation. And in all cases here, we basically achieve our results by first deriving a linear or quadratic system due to the public-private key relations. And then, given the leakage, we eliminate variables from these systems. And then we solve it by Gaussian elimination or by linearization. So in the by case, let us just quickly have a look how this worked. So as we already saw, the by secret key fulfills this linear relation, A times S is equal to E. And yeah, our attack basically simply shows that you don't need to know S or E, just any n/2 coordinates suffice. Because yeah, as long as you have less than n/2's question marks, you can you have less than n/2 unknowns in this linear system. Maybe more interestingly, in the compact case, so the compact case, as we said, it encodes the 1 positions of the secret key. So we have these blocks of size log n, which encode 1 index where the secret key is 1. And then we have square root n of many of them. And now our attack first enumerates the erasures per block, which gives you a list of candidates where the secret key might be 1. And then, of course, if something is not appearing among this list, then it must be 0. So that means as long as the list is smaller than n/2, we know n/2 0 positions and can eliminate n/2 variables from this system, and can then again solve via Gaussian elimination. Exactly. Yes, and we let us look into the practical bounds. So here the question is how big can the number of erasures be to recover below a certain threshold? Here we use 60-bit complexity for the category 1 parameter sets in this setting here. Yeah. And first, if you perform an enumeration only, then you can recover basically less than 0.01, so 1% erasures you can tolerate. And we see that those are way higher here. And again, we see the redundancy reflected. Unfortunately, I don't have the time to go into all the details, but let me just briefly sketch what kind of techniques we used to obtain our results. So in the rainbow case, we recover the first layer by modeling a linear system, and the second layer by solving a quadratic system. In the by case, we use something similar as in the asymptotic setting, what we have seen, like an accelerated ISD, which is modified to a non-polynomial setting. Yeah, and a few practical tweaks. And in the entry case, we use lattice reduction, where we apply some dimension reduction by using the known leakage. So let us now briefly cover the error model. So in the error model, we still have a secret key of n bits, and we get a knowledge of an erroneous version of this key, where some bits might be flipped, so indicated by these orange bits here. But of course, the positions are not known. It's just to easier checks that there are some bits flipped. And then we differentiate two like submodels, where we have one symmetric model where 0 flips to a 1 with the same probability as a 1 flips to a 0, and one asymmetric model where one of the probabilities is very small and the other is ranging over different values. And this is the asymmetric model, and it's basically motivated by some physical observations. Let's cover the asymptotic bounds first. So we have again the different settings, and we see how many errors we can tolerate to still recover in polynomial time. Again, an enumeration approach here would only allow for a constant number of errors because we don't know the position of the errors. So the complexity is n choose the number of errors, which is only polynomial for a constant amount of errors. And we see that all attacks basically allow for more errors to be recovered. And yeah, maybe most interestingly, in the bike case, the compact model actually allows to recover more errors than the standard setting. We will see in a second why this is the case. And also technique-wise, we use information set decoding in all cases to achieve our results. The only outlier here is the full key recovery in the rainbow case, where we model, we solve a quadratic system to recover the inner UV key. Yeah, let's cover the attacks on bike maybe. So in the standard setting, we get this erroneous version which is just the n-bit key, which basically is usually very sparse. So it includes only a few amount of ones here, maybe as a few more due to the bit flips that occurred. But still, the technique in a nutshell is to solve it via ISD, but sample the 0 coordinates only from the zeros of this erroneous version, because these are more likely to encode real zeros of the secret key. And in the compact case, we have again this blocks of size log n and square root many of them, encoding the indices where the secret key is 1. And then we first enumerate small weight errors on each block to get the list of candidates. And this list of candidates can be seen as a list of coordinates where the secret key has a higher probability to be 1. So we solve then via ISD, but not sampling from this list of candidates. And since we are able to manipulate the size of this list by changing the error we enumerate, we have this advantage. We have this advantage in the amount of errors we can tolerate. So last but not least, let's cover the practical bounds in the error model. So here again, we consider the category 1 parameters for all 3 schemes, and we differentiate here the symmetric and the asymmetric model. So for the asymptotic bounds, we only consider the more difficult symmetric model, so where 1 and 0 flip with the same probability. But in the practical setting, it can make a huge difference. So we also consider this asymmetric model. And again, we have the threshold of 60-bit complexity. And if you consider enumeration attacks only, then usually you can handle, depending on symmetric or asymmetric, 1% to 0.1% in the symmetric model. And technique-wise, we're basically quite similar to what we did in the erasure model. Here we used maybe in the intro case, we found that some combinatorial attacks actually perform better, which were recently introduced, and not always a lattice reduction is the best choice. Yes. So as a conclusion, we give non-trivial polynomial time key recovery attacks in all cases, and for the practical bounds or for the practical setting, we find even higher bounds. And actually, these results are comparable to what we know about classical schemes like RSA, and so we can safely conclude that post-quantum candidates do not per se enjoy leakage resistance. So thank you very much. The paper is online for all the details, and I'm happy to take questions.
Thank you for the nice presentation. Is there anybody here who has a question? I see some people. Oh, yeah. Please just go to the microphone, I guess, if that's possible.
Hi, thanks for the talk. For the compressed version of the bike key, you mentioned that you could do recovery with n over 11 erasures. Where did 11 come from? Seems like kind of a random number.
Yeah, it's true. It's actually I just rounded a little bit to make it easier for the slides, but basically you need to ensure that the number of erasures per block, so per these log n blocks, that this is not too high because we enumerate the erasures there. So we just need to ensure that it always stays low enough, because it is like an exponential blow up if you enumerate there. So you have the amount of candidates you generate per block is 2 to the number of erasures per block. So this needs to be lower than, so that the sum over all of them is smaller than n/2. And yeah, so it's just the proof that yields like this 11 there to bound it sufficiently. But in practice, we see that the amount is actually way higher. So there's a huge gap between what we can prove and what we see in practice. In practice, we can almost recover like 50% as in the as in the standard case.
Busy. Oh wait, thank you.
Anyone else?
Oh, yes, I got a question. Is it assumed that we know the positions of rightly guessed bits?
Sorry, the positions of what?
Of bits that are guessed correctly.
Sorry, I'm not, so the positions in the erasure case, so there's the erasure model and the error model. In the erasure model, we know the positions of these green parts of the secret key and this question mark covered. And you know the value of the ones which were green in the graphic, and the ones with question marks, you don't know the value. And in the error case, you don't know the position of the flip bits. Otherwise, it would be pretty easy.
Oh, I see. Thank you.
Okay, I guess if there are no more questions right now, we can continue with the next talk. So thanks to the speaker again. As usual, while they set up the tech stuff, I will introduce the next talk. This is another talk on post-quantum primitives. Its title is Improving Support Miners Rank Attacks with Applications to Gems in Rainbow, which are two post-quantum primitives. And the authors are Pierre Birot, who's here and about to give the talk, Javier Rebel, again, Daniel Smith-Tone, Ray Perlner, Daniel Cabarcas, I guess, and John Boehner. So please go ahead whenever you're ready.
Hi, so I'm Pierre from INRIA Paris and Sorbonne University, and I will be presenting some cryptanalysis on gems and rainbow, which were like former round 3 NIST candidates. And this is joint work with John Boehner, Daniel Cabarcas, Ray Perlner, Daniel Smith-Tone, and Javier Verbel. So gems and rainbow are both multivariate signature schemes. So this means that they rely on multivariate maps. So the secret key is some polynomial system P, which looks like a random system, so it should be hard to invert. And the secret key is some extra information which would allow a legitimate user to efficiently find preimages of P. So you start from what I call big F, which is the central map. It's a polynomial system which is easy to invert this time. And you also have some linear maps T and U, such that you have the equality P is equal to the composition of T, F, and U. And basically, the main difference between gems and rainbow is how this big F map is constructed. So GEMS relies on the very old HFE construction. And Rainbow, you have already heard about it several times this week. It is a variant of the oil and vinegar signature scheme. So even though those two constructions are quite different, both schemes are vulnerable to what we call rank attacks. So a rank attack is a particular type of key recovery attack by solving an instance of the min rank problem. So in min rank, you're given a set of public matrices M1 to MK, which are over FQ. And your goal is to find some rank small d linear combination between these matrices. And here in the more general version of the problem, it will be really helpful to ask that these secret entries Xi's lie in big L, which is an extension field of FQ. And actually, most of the recent progress in the cryptanalysis on GEMS and Rainbow came from improving this type of rank attacks. You have last year at Eurocrypt the rectangular min rank attack by Balance, and also on HFE variants, and therefore on GEMS, you had this work by Tao, Peljolt, and Ding at Crypto last year, which earned the base paper award. And in both cases, what they do is that they find easier min rank instances than the ones which were used in former rank attacks. So this is not enough to come up, of course, with a complete attack, because it remains to solve the instance once you have the min rank problem. And in this area as well, there was another breakthrough, which is called support minors, which was proposed by Bardet et al. And support minors is a new algebraic modeling to solve the min rank problem. So to describe it, I start from M, which is the secret rank D matrix. So of course you don't know it. And you write it as a product D times C like this, where the matrix C has only D rows. And from this equality, if you take your row or J of M, you notice that this row is also in the row space of C. So this means that if I construct this matrix like this, which is simply you stack your row with your matrix C, this is a matrix with D+1 rows, but the rank can be at most D. And then there is a very easy way to generate the equation, is to write that all the maximal minors of Cj, which are of size D+1, are 0. And you can do this for any row index J. So in this way, you get your system Q, which is the support minor system. And this is clearly a nonlinear system, because like you have minors, there is no reason why the equation are linear. So a naive way to solve it is to linearize. And of course, it will fail if you don't have enough equations compared to the number of monomials. But in this case, you can still try to apply what is called XL, which is like you multiply the equations by monomials of higher degree, and you try to linearize again. And in both cases, in fact, you are left with computing the kernel of some matrix MQ, which is directly related to your initial system. So our first contribution is this paper is to propose an improved attack on HFE variants and GEMS, which is based on this very same support minor system. So before starting, I need to give a bit of background on HFE. So this is what we call a big field scheme. So to construct our central map, we start from FQN, which is an extension field. And we also use phi, which is some isomorphism. So then we go from our initial space to the extension field by apply I phi. And then over the big field, we have a small f, which is what I call the HFE polynomial. This is a univariate polynomial of degree big D. And essentially, this big D is what makes the schemes efficient or not. And then finally, you will apply phi minus 1 to go back to your initial space. So here, the important thing is that your polynomial small f is over the big field, but your public polynomials are over the small field. And finally, GEMS is what we call an HFE variant, because this is this plain HFE construction to which you add some modifiers. And so this explains that your scheme also has some extra parameters, A and B. So actually, our attack will rely on the same min-rank problem which was introduced by Tao et al. Last year at Crypto. So here, the target rank is small d, which is the logarithm of the degree of the univariate polynomial. And this attack is by constructing some matrices over FQ, which are like M1 to Mn plus V, that you can easily generate from the public key. And now it turns out that you have some rank small d linear combination between these matrices. But if you take your solution vector U over the extension field FQN, and basically from the knowledge of any such U, it will be very easy to recover the security of the scheme in like polynomial time. So here, the important thing to remember is that your matrices are over FQ, but as I said, the solution is over FQN. And this is really crucial because if you have a low rank matrix like this, if you apply the Frobenius map X to the X power Q on the entries, you will get another solution. And basically, all the rank D solutions that we expect are of this form. So this means that even if you fix one UI variable to 1 in your system, you still get n solution, which is huge. And this means that the linearization techniques or Excel that I mentioned earlier, you cannot really apply them because this would mean that you would have a large kernel in your matrix. It would be infeasible to recover your solution. And this was a bit an issue because we really wanted to apply the support minors modeling, which is usually used to solve min-rank. So in fact, we'll see that our attack will be, instead of linearizing a system, it will be like more convenient to see that as a form of Grosvenor-resist computation. So here we start from this matrix, and in fact, we are going to restrict ourselves to only a subset of columns in there. So also there is a very important property of support minors, which was already pointed out in the initial paper, is that this system is a bilinear system. So in fact, your set of monomials is this one. So the set of monomials is a very particular shape. And here, CT refers to what? To a maximal minor of the matrix C. So instead of having the entries of the secret matrix C as variables, we'll take the maximal minors. And in fact, we can see that there is no ambiguity by doing that. And it turns out that in the case of gems, we have more equations than this number of monomials. But I said already that it was not possible to linearize, but still, this means that all equations cannot be linearly independent. And actually, as the number of solutions was equal to n, we assume that the rank defect in our system is also equal to n, and basically we have this equality for the dimension. So now we have already seen that in HFE, I could fix one UI variable to 1. And in fact, in our attack, what we do is that we have another degree of freedom on the other block of variables, which really comes from the structure of the support minor system. And by fixing these two variables, we notice that our initial set of degree 2 monomials is reduced to this one. Now we have less degree 2 monomials. And once again, we notice that we still have an inequality of the same kind between the number of equations and the number of monomials. So here, this means that we are going to kill degree 2 monomials in some equations. And in particular, this means that by performing Gaussian elimination, we can generate a smaller system L, which is only made of linear equations. And this is really helpful because several times you have seen that each time that you have a linear equation, you can use it to remove some variables in your initial system. And here it's even more advantageous because we analyze the shape of such system L, and also we have plenty of equations. So we can make sure that we kill all CT variables in our system, which were a bit the nasty part. And by substitution, if you substitute these linear equations in your initial system, you can produce a second system S, which is quadratic in the UI variables because I removed all the CT variables. And it has a very nice property. It is very overdefined. This means that we have a lot more equations than variables. So finally, how do we solve this S? Well, don't have a more clever way to do that, applying Grosvenor basis, which is something really like costly in general. But here, since our system, once again, it's very overdefined, in fact, we can show that the Grosvenor basis computation terminates really early. It terminates in degree 2. So basically, this means that we don't go at higher degree. And we have a small condition here, but in fact, it turns out that on the parameter of James, this condition is very easily met. So to sum up, our first contribution is like we have our attack, which is first, we generate this system L by performing the Gaussian elimination, and then we have a second step, which is just Grosvenor basis. But I said that this second step is like cheap. So in fact, it turns out that the dominant cost in the attack is the first one. So here you have the comparison between our attack and the one of Tao et al. So you already see that the initial attack was quite efficient on the parameters. But still, it has been shown that also you could repair gems, you could still do it, you could still make it against this Tao attack. So also, Tao et al. Already proposed to use support minors. So if you have a column corresponding to this complexity, but they provide absolutely no complexity analysis. So this is just a pure conjecture. And you see that our attack, first, we have like a proof of the complexity formula. And also, it's much more powerful than the former attacks. And basically, this makes that the attempts to repair gems, which were like immune to the attack of Tao et al., now they are broken as well. And we believe that coming up with an HFE time scheme, which will resist to our attack, would be quite inefficient. So for our second contribution, we are not restricted to gems and HFE anymore. Like here, you have to imagine a random min-rank instance that you want to solve. And we are going to solve it using support minors. And here, what we try to do is trying to analyze the memory access cost, which can occur when we perform this kind of attacks. So the initial motivation for this work was Rainbow and the rectangular min-rank attack, which was presented at Eurocrypt last year. This is a min-rank attack. Because this attack clearly breaks the parameters of the scheme in the RAM model, so where you don't really care about all these memory access costs. But it's perfectly legitimate to try to include them in the cost of the attack, because especially for algebraic attacks, it's known that it can be a bottleneck. So this is what was done in the Rainbow response by the Rainbow team. So in fact, they proposed to use the 2D nearest neighbor model to analyze this cost. And in fact, if they assume some randomness on the memory access patterns which occur in this attack, they show that the attack by Balance was above the security level. And our method was, what if these memory access patterns are not random? Like, is the attack really a threat against the scheme? So first, I need to explain a bit more what is this model. So initially, it comes from the n through prime submissions, and it is essentially based on energy consumption. So in this model, your memory locations are evenly distributed over a 2D surface, and also this density is limited. So this means that the main overhead is essentially proportional to the distance which is covered by bit of data, but you also have to take into account a second cost, which is the distance traveled by memory addresses. So what sort of computation do we have to perform in this kind of attack? I recall you that we have our matrix MQ, which was associated to the support minor system, and we want to compute its kernel. So we do that with the Wiedemann algorithm, which is essentially like several matrix vector products like this. And here, it's a bit counterintuitive, but even if our matrix MQ is large, this is not the bottleneck of the computation because it's also very sparse. So in fact, we are going to generate all the entries on the fly, and we don't need to store the matrix. However, our vector V will be stored in memory, and it will be the most costly part to store the coefficients of V and also access the coefficients of V each time we need them for the computation. So now to compute our matrix vector products, in fact, it's easily seen to be several rho times V products. And now I will explain how naively you compute such a product. So in fact, you have a rho times vector product. This is the same thing as more or less the sum of FQ times FQ terms. And each non-zero term will correspond to a non-zero coefficient in your row. But you know, since your matrix comes from an algebraic system, in fact, each non-zero coefficient in the row is directly related to the non-coefficient in your initial system. And then for each of these non-zero coefficients, the central processor will have to send a read request to the memory locations. But here the memory is of the size of the vector, and the vector is very big, so this is costly. So the very high overview of our approach is try to cut this main memory into small pieces, so we have a partition pie like this. And in fact, instead of having a central processor which computes this rho times V product, now we have a local processor which computes what I call a partial sum rho pi I times V pi I. And in fact, from these partial sums, it will the only remaining part is to gather them by a central accumulator, which will sum them to obtain our final product. So why it's Invintageous? Because first, using the structure of our system, we can make that only a small number of partitions will be responsible for one rho times V product. So this means that only a few partial sums need to be sent long distance. So this is quite, we try to reduce the cost like this. Another advantage is that even if the local processor does exactly the same operations as the central processor of before, all the operations are done locally. So we have no extra cost like this. And also there is another optimization which comes from the fact that some equations have same non-zero positions because some polynomials have the same monomial content. And so from that, this means that the memory access patterns in your attack will be the same. So it was quite helpful to group all these equations in a batch so that in fact each call to the memory of the size of the element of the partition, we do it only once per batch. And similarly, memory addresses will be sent only once per batch. So there are things that I don't really have time to discuss. The attack by Balance also uses the p=0 equations, which are not mean rank equations, which are simply equations which come from the public key of Rainbow. And we show how to include them in the model. And in fact, they are very helpful because from a memory point of view, they are only tackled by only one local processor. So here, there is no need to gather the partial sums by the central accumulator. Also, you may say that, yeah, you have introduced several processors a bit everywhere. So maybe there is some extra cost. Maybe you have to think about the cost of parallelization, etc. And so if you want, some of these costs are neglected, and we discuss about that in more details in the paper. So finally, we can see a bit what it can give for the rainbow parameters. So here, you have the complexity of the attack if you don't take memory into account. So in the RAM model, you see that indeed it's below the security. And here you have two costs in the 2D model. So the one is more or less the one claimed by the repo response if you have like random memory access patterns. And here is the one obtained with our strategy. So you see that mostly you gain over 20 bits each time. And hopefully, or sadly for the designers, we go below the security target. So here I really don't claim that this cost is really accurate. This is mostly to say that we cannot just say that the scheme is saved just using like memory, because the situation is probably in between, or maybe like even smaller or maybe larger, we don't know. But this is just to point out that things are probably more complicated. And in any case, you probably know that Rainbow now is broken on a laptop, so such a speculation is maybe not needed for Rainbow. I don't know. Personally, I think it's not needed. But I want to point out the fact that all this analysis is really dependent on support minors and not really on Rainbow. So this means that you could apply it to other min-rank attacks, which uses support minors as a subroutine. And there are still like constructions which rely on the plain min-rank problem and which are not Rainbow. So thank you for your attention. I would be happy to answer questions.
Thank you for this very interesting talk with plenty of nice results. Are there any questions in the audience here? Okay, I also don't see any questions on Zoom. I have one question I'm kind of wondering about, which is that there are rumors that maybe plain UOV without the Rainbow structure will be submitted to the next NIST call. Does this analysis impact the parameter choices for that, or is it just not really applicable?
In fact, as far as I know, I don't think for the moment it's possible, but I presented what is called rank attacks, and so far rank attacks are not a threat against UOV. There is also an interesting scheme which is called Mayo, which is a variant of UOV. Maybe it will be submitted, I don't know. But so far, they don't have any relationship with rank attacks. Like the schemes based on min rank I was mentioning is more like a kind of authentication scheme which uses the knowledge of the solution of the min rank problem to build like zero knowledge stuff, etc. So this is another kind of, it's not signature, it's not really, it's really different.
Okay, thank you. I guess that ends this session. So let's first thank the speaker again.